Hi everyone. So this talk is about a project that it's an innovation fund project. It lasts 2 years and we've got another 6 months to go. And we're just at the moment getting all the results together. So you'll be among the first people to hear what we found out. And this project is very much a proof of concept type project. We're trialing a new method to answer questions that have been very difficult to answer so far because we didn't have the tools to do it. And this project is about connectivity, which is a big theme for the Sustainable Seas Challenge, because we need to know how things are connected within ecosystems and between ecosystems. Perhaps the most obvious example of connectivity is how rivers carry a lot of material and water and other stuff from the land and carry it to the sea. And we know that globally this input is huge. And in New Zealand alone, we know that there's about 200 million tons of sediment being washed into the sea every year. The current thinking is that most of this stuff gets either settled or taken out of the system somehow or used up in a shallow water environment. So you can think of, if you look at the map on the right side, this red area is the Continental Shelf, and this acts more or less as a barrier for things coming out of the rivers, and they actually just sort of get blocked by that shelf before it gets to the deep sea. So the thinking is that there's not much connectivity going on between land and the deep sea because of that continental shelf. However, from historical records going back thousands of years, we know that there used to be a lot more stuff going from the land to the deep ocean, and that was because at some point the sea level was a lot lower, and there was hardly any continental shelf, so no barrier to block this transport. Obviously now we do have the continental shelves, but what we do have also are canyons, and these canyons are basically, we can think of them as shortcuts. Geologists know that canyons carry a lot of sediment. We don't know about the organic matter because it's a bit harder to trace. And we happen to have, as Robin said, over 270 odd of these canyons / channels around the country. They're shown on that map. And so the potential for connectivity is quite high. And, you know, New Zealand has a lot of canyons, but a lot of other countries and nations have canyons as well surrounding their coastlines. So as part of this project, we wanted to look at 2 of these canyons because obviously we can't look at them all. And try and figure out how much organic matter makes it from watersheds and catchments down into the deep sea. And we do that using a newly developed chemical tracer technique, which I'll talk about a bit more in a minute. So these are the 2 canyons we focused on. We chose them because they're quite different. The first one on the east coast is the Kaikoura Canyon, and you might see there that it goes quite far in, close to the shore, and it's also quite steep and it's relatively wide. And the currents in this area on the east coast, shown by the blue arrow, goes from south to north. And so we thought maybe the stuff that comes down these watersheds highlighted in purple ends up in the canyon. And so these are the watersheds we decided to focus on. On the west coast, we looked at the Hokitika Canyon, which is quite different in that it's further away from the shore. It's it's not as steep. It's quite narrow and windy. And we thought maybe because they have such different shapes, we'll see very different things happening in these two canyons. And again, we chose 2 watersheds, the Hokitika River and the Whataroa River, which have quite a lot of water going down them. And actually, if you look at the combined watersheds on the west coast, they carry about 10 times as much water and suspended sediment as the watersheds on the east coast. So a lot of things that are different. So we didn't go out to sea to do this sampling. We needed to find a mud that was purely marine. So we had to get mud, or find mud that was from way offshore. And on this side of the coast, on the east coast, we took samples from Chatham Rise, and we just raided the NIWA freezers and found what we were after, luckily. And so this mud was, okay, this is our 100% marine mud, and this is how it looks from a chemical perspective. And then there's the purely terrestrial mud, which we got from the riverbeds. You see the yellow symbols, and we picked 3 rivers there to sample. And then we looked at sediments from the canyon, again from the freezers, and we said, okay, does the mud from the canyon look like mostly like marine mud, or does it look like riverbed mud, or somewhere in between? That's the basic idea of this method. And we applied the same approach for the west coast. Again, offshore mud in green, purely marine, and then the 2 river that we focused on, and in the red, samples from the canyon going from about 200 meters to 2,000 meters. And a similar range of depth, water depth, was sampled on the east coast. So we got going fairly deep. Now, I said we didn't sample. That's not quite true. We did some riverbed sampling, and this is Max Gibbs, and who went out there with Andrew Swales, both from NIWA and Hamilton. And Max is the one who developed the chemical tracer technique as well. And that's fairly straightforward stuff. The sampling was pretty easy. I shouldn't say that. Maybe there's quite a lot to it. I just don't know. I wasn't there. But they took mud from riverbed at different spots so that they could characterize the sediment in these rivers. Sounded like quite a fun road trip, actually. And just a quick word about the chemical tracer technique. We use 2, and one is called the bulk isotope technique, which has been around for a while, and we just wanted to use it because we can. And the second one is called a compound-specific isotope technique, and that's the one that Max developed. And he developed it to look at the different input of sediment from, say, dairy or forestry to estuaries. And we decided to use that technique and apply it to the deep sea and see if it works. So some results. So don't worry about the numbers. What matters really is where the point sits, the points sit relative to each other. So on the bottom left, you have the riverbed sample signature. And at the opposite side of the graph on the top right is the offshore marine stuff. And in between, as you might expect, is the canyon mud. And each of these dots is the different site along the canyon. And some of these sites are more similar to marine mud, and others are really like 50-50 between riverbed and offshore marine samples. And if you put these data into a mixing model, you get these numbers. So I've mapped the numbers on the canyon, a map of the canyon. So if you go up the upper parts of the canyon, about 50% of the organic matter comes from rivers. But this contribution decreases relatively rapidly as you go down into the canyon to about 30% and 13% at about 1,500 meters. So there is organic matter coming from the rivers in the canyon, but it decreases quite rapidly. Just for an idea of scale, the distance between the furthest canyon site to the coast is about 25 kilometers. And another thing we observed is that the sites with the highest amount of terrestrial derived organic matter are the sites that have the most animals. It doesn't mean that there's a causal relationship, but it's interesting nonetheless that there might be a relationship there, meaning that terrestrial organic matter might be fueling the food web in the canyon. Now looking at the same kind of graphs, but for Hokitika, the picture there is a bit different. We still have the offshore marine on the top right. We still have the riverbed stuff, the yellow points on the bottom left, but the river sample, the canyon samples, overlap a lot with the riverbed samples. So that means that there's a fair amount of terrestrial matter in there. And if you put this on a map, this time we see that the amount of organic matter is high everywhere along the canyon. So from the very top at 200 meters all the way down to 2,000 meters depth. And that distance between the coast and that really deep site on the left is about 200 kilometers. So this stuff seems to be traveling quite a long distance, which was interesting because it's not what we were expecting. I'll just discuss that here at the end. Here we didn't see a relationship between the input of terrestrial organic matter and the number of animals in the seabed. So clearly the relationship doesn't always apply, and there are different things going on in this canyon. Now some results. This one is the new technique that Max developed, and this one is interesting because it allows us to differentiate between the different rivers, so we can tell which river is contributing organic matter to the sediment of a particular site. And we have the Kaikoura and Hokitika Canyon there. On each site is ordered from shallow to deep, from left to right. And in the Kaikoura Canyon, you can see a bit of marine input on the left-hand side in blue, and that increases to about 100% as you get in the deepest site. And then the orange and yellow and gray bars show the different contributions of the different rivers, which are not the same. And there's one of the rivers, the Waia River, for some reason, doesn't contribute much at all to these sediments. In Hokitika, same story, well, not same story actually. The marine contribution is very low as you go from shallow to deep. Similar results as to the bulk isotope results I just showed you, and the contribution of the different rivers varies. In this case, the Whataroa River seems to be dominating at all the sites, which is interesting because it's the one that's furthest away from the canyon. But we've got an idea as to why that might be. So, in summary, we did find that there is an input, quite significant input of land-derived organic matter in the canyons, but they're not the same. It seems Hokitika is a lot more efficient at it than the Kaikoura Canyon. And it's probably a direct result of the input of water and suspended sediment on the west coast, which is much higher. There's a lot more rain, a lot more water making it through to the coast than on the east coast. So we weren't thinking about that at all at the beginning. We were thinking about canyon shape and morphology, and it turns out it might have very little to do with connectivity in the end. Turns out the chemical tracer technique works very well for the deep sea, so we're quite keen to some future apply it to other questions, other canyons, other places. And it revealed an interesting difference in between rivers. Not all rivers contribute to this connectivity. And we suspect it has to do with ocean currents. Now, this project has got another aspect to it. We want to try and extrapolate the results we've got to other canyons. And basically, we've got a database that includes all sorts of biological and physical data, and using it and using the results that we've got, we want to try and figure out where else around the country there might be a lot of connectivity going on. And it might just be that it's in the vicinity of those really big rivers. It might be quite simple. And ocean currents are interesting, where they certainly play a role, or seem to be playing a role, in the way different rivers might flow into canyons. And other questions which are for another project are, what does it mean in terms of all this organic matter sinking down into the deep sea is effectively being taken out of circulation and so sort of acts as a carbon sink, and how significant might this carbon sink be? And if canyons can focus organic matter, then no doubt they will be focusing and accumulating pollution as well, things like plastics and chemicals. And that's a bit of a worry, actually. And as far as implications for ecosystem-based management, there's a few. It means that the footprint that we have doesn't extend just to the coast and the estuaries, where the impacts are a bit more obvious. It also goes down to deep waters, where we don't see what's happening. It's a lot harder to go in and look at the impacts. And it might be that change in land use, both during the last few centuries as well as now, will be impacting communities in the deep sea. And these communities are not used to change. These deep sea communities, all the processes down there occur a lot more slowly than they do in the shallow water system, so it might not take very much at all to take them over the edge. And so this idea that you will have heard about ki uta ki tai, or mountains to the sea, should probably be extended to the deep sea, so mountains to the deep sea. And that is all I've got. Thank you very much.
Okay. Thank you very much, Daniel. That's really interesting. I love that it's just so connected, and you didn't necessarily expect it to be the way that it is, which every marine scientist I talk to, when they say it wasn't what we expected, but it's marine science, so we kind of did. So we have a question from Catherine Short, who asks, what does the international literature say about the connectivity between terrestrial watersheds and submarine canyons?
It depends what you mean by connectivity. The geologists have been doing it for a long time. They know that sediment is constantly being carried down the canyons. So from that perspective, there's a lot of literature on this. But what we're interested in is tracing the organic matter, which is important from an ecological point of view because it means transport of food, transport of carbon and nutrients down into canyons. And from that point of view, there's very little, which is why we were keen to develop and apply this new method.
Are there any other questions from either in the room or elsewhere around the room? Craig, let's ask again.
Nice one, Daniel. For the West Coast situation, have you talked to Joe O'Callaghan? So we had a string of moorings down that coast. One of the questions we were looking at was the freshwater halos, more from Fiordland, but there was some moorings a bit to the north, and then trying to connect that to what was ending up going down the canyon, not in terms of sediment, but in terms of water column. It will be good to, if you've not chatted with Joe, there's a story there.
We've been talking about it, so
yeah,
we'll be meaning to. Yes.
From our perspective, the trick is we're looking at the freshwater halo, so that actually sits on top, and then it's processing the suspended sediment, and then that's dropping out. So there's kind of like an intermediate step rather than just starting in the river down to the seabed and out.
Yeah, cool. Okay. Yeah. No, that's definitely something we need to look into, is the physics of it.
Another one, someone's coming down to the microphone. And Nelson, I'm looking at you just in case you're waving, but you're quiet this time.
So the way that you set it up was you had multiple different things happening in the two different canyons, but then you also had different amounts of water flowing into the canyons, is that right? Yes. So I'm trying to just make sure I understood your conclusion. So was it the water that was the difference, or was it the type of canyons?
They were both different, and
okay.
We can't tell the difference. We can't tell which factor is the one that's driving the difference. Mm-hmm. It could be that, but my expectation at the beginning, and the other people involved in the project might have had their own ideas, but my idea was that Kaikoura Canyon comes in very close to the land, and so anything that is flowing past is more likely to get intercepted by the canyon and then just make its way down eventually. So I was expecting a whole lot of terrestrial organic matter down in that canyon, more or less along the entire canyon, and then less on the west coast, because I was thinking mostly of the morphology. But turns out that's not the case at all. So it's more or less the opposite. So and then seeing the difference in rainfall and the suspended sediment yield being so large, I'm suspecting that maybe this is sort of the easiest way to explain the difference. But we've only got two canyons, so.
Yeah. Is there? I know it's a huge project, but is there a plan to try and isolate any of those factors?
No. We've got 6 months to go, and we're struggling to put it all together. Obviously, we'd like to, because we'll be generating predictions from this canyon classification thing, then it would be cool to go and test those predictions.
Thank you.
We've got a question from Don Neal, which says, it seems from recent studies that Kaikoura sedimentation is episodic, connected to seismic activity, correct? Does the same apply to Hokitika?
Well, I don't know much about this personally, and Scott, who's in the room, would know more. But you had an idea about this, didn't you, Scott?
Yeah, no, I suspect that's possibly a factor, that Kaikoura is more of a system that's driven by episodic processes, driven by the earthquake generation of turbidity currents down the canyon, whereas Hokitika and possibly the other West Coast canyons are more driven by the day-to-day and seasonal effects of large rivers flowing, pushing sediment out onto the shelf and then down the canyon system. So more, if you like, a more continuous process.
I think one thing that we could do is to age, well, we can't do it as part of this project, but one way to answer that would be to try and age the organic matter that we find. Then you get yeah.
Okay, so questions beget more questions.
Yes, always.
Okay. Unless anyone's got one final question, I think that we are finished. I'll just say thank you very much again to our speakers. Thank you, Daniel. That was great. Lovely round. And thank you to everyone who stuck with us. I did look at how many people were signed on at the beginning and how many were signed up at the end, and you've all been great and sticking with us. So thank you very much. We'll see you next time. Keep posted for alerts. The next one I expect will be in about a month to 6 weeks. Okay. Kia ora.
Thanks.